We're going to use the example of the spring mass damper to show an example of how we change from a ordinary differential equation into a state space model. So these are two different ways of representing the same system. And the main difference that you can think about is that the ordinary differential equation, in this case, is a second order system. And our goal for a state space representation is that we will be deriving a single order differential equation, but that will have multiple states. In this case, because this is an order 2 differential equation, we will then change it into a first order differential equation with 2 states, so that the 2 in both of those cases is important. That's linked. So the first step that we do is we define state variables. Typically, we take the first one, x1, to be the output, y, the variable of our differential equation. And then we define another one that is the derivative of that state. And so then our new state, x of t, is a vector that has 2 components, x1 and x2. And so the elegant part of this is that in the second step, we now write out the derivative of each of these components of the state. So the derivative of x1 is just y dot. And the cool part about it is that that is the same thing as what we defined our second state to be. That's x2 of t. So x1 dot is equal to x2. And x2 dot is equal to y double dot. And so now this is where, and this is always going to happen, you're going to go back to the original differential equation and write out y double dot in terms of y dot and y. And in this case also u. And so if we solve for y double dot in the original differential equation, it's simply just minus b, and then we have to divide by m, b over m, y dot, minus k over m y, plus 1 over m times u. And now we get to replace y dot and y in terms of the new variables that we've defined, x1 and x2. So y dot is x2, and y is x1. And so notice what we've done now is now we have x1 dot and x2 dot written in terms of only x1 and x2. There's no more y's involved. And so this is what allows us to rewrite the original differential equation into essentially a system of first order differential equations. And so if we do that, let's just write those in vector form. So that means x1 dot is equal to x2, and x2 dot is equal to that expression that we found, minus b over m x2 minus k over m x1 plus 1 over m u. So now we've just written that in vector form, and now our goal is to write this in matrix form. And so we do that by extracting x1 and x2 from these expressions and writing that in terms of a matrix multiplication of a matrix A multiplied by the vector of the states, x1 and x2. So we have x dot, which is x1 dot and x2 dot, a vector of x1 dot and x2 dot, and that's equal to this matrix A multiplied by that same vector x1, x2. And so the way that we can write that first equation, essentially in this case the first equation is just x1 dot is equal to x2, is to write in the first row of A, we make the first element 0 and the second element 1. And so that means when we do the matrix multiplication, the first row of the matrix multiplication will just be x2. Similarly, in the second line, you'll notice the second row of A, we put in minus k over m as the first element and minus b over m as the second element. So that minus k over m multiplies x1 in the matrix multiplication, and the minus b over m multiplies x2. And so the only thing that we're left with is to define the leftover part, which is 1 over m u of t. And that is in a new matrix, which we'll call capital B. And finally, in order to represent the output of the system of the differential equation, which was y, we just need to write y in terms of the states x1 and x2. And in this case, that's very simple. y is simply just x1. And so we define a matrix C, which is 1, 0. And when we do that matrix multiplication with the vector x1, x2, that just gives us back x1. So now what I'd like you to do before class is to try this same process with new variables. So I'm just calling them z1 and z2 instead of x1 and x2, just to help you think about it. So define z1 as y and z2 as y plus y dot. So this is going to be a little bit different, but you should be able to step through the same process of steps 1, 2, 3, and 4 to write a state space representation, and we'll talk about this in class.